Welcome everyone to this month's online seminar of the Working Group on Active B-Stars. It's always a pleasure to present interesting talks to you. This month, we're very lucky to have a presentation by Dr. Joey Mombarg, who completed his bachelor's and master's degrees at Radboud University Nijmegen, then completed a PhD under the supervision of Connie Ertz at KU Leuven, and is currently a postdoc at the IRAP in Toulouse. And today, Joy is going to be talking to us about evolutionary modeling of B star formation. So with no further ado, Joy, please take it away.
Yes, thank you, Alex. Good pronunciation, by the way. So let me share my screen. Okay, good. So hi everyone. Thanks for tuning in to this seminar. So in some of the versions of the abstract, I think the part that said actually explained what I was going to talk about was missing. So it kind of maybe sound like I was just going to bash 1D stellar models for the next hour. But of course, if you can guess from the title, I'm going to talk about the endeavors that we do here in Toulouse to compute stellar evolution in two spatial dimensions. So I'm just going to start by introducing what kind of physics we put into these models, and then show you a comparison to a real star. And then for the final part, I will kind of discuss what these 2D models imply for the formation of single BE stars. So I'm part of the larger ANM Massif project across France. So as I explained, the node here in Toulouse focuses on doing 2D stellar evolution models. And we have a node in Paris that focuses on the stellar pulsation code top. It's a 2D stellar pulsation code that can be coupled to the stellar structure models. And then there's a node in Nice, and that focus more on the observational part, and particularly on interferometry. So yeah, I'll start by just giving you my working definition of a BE star, which is a star of spectral type B that rotates sufficiently fast that it can form a decretion disk. And so it's also kind of debated what fraction of critical rotation velocity is actually needed to form such a disk. So these are very interesting objects for us to test our current knowledge on how we think the rotation in stars evolves. So probably the most dominant formation channel for these BE stars is the binary channel. So that involves a companion and transfer of angular momentum transport. But there's also single formation channels being proposed. And so that raises the question, how do we then spin up a star to critical rotation during the main sequence, for example? Or in which circumstances could we form single BE stars? So that's kind of the topic of this seminar today. Yeah, so here in this cartoon, I'm showing you the surface deformation due to the centrifugal force as a fraction of the critical rotation rate. And so as you can see already at around 50% critical, the star is not really spherical anymore. So then we should wonder if the 1D stellar evolution models that we all know and love can still be trusted at such high rotation rates or high fractions of the critical rotation rate. So yeah, the 2D models I'm going to talk about today are computed with the STER code, which stands for Évolution stellaire en rotation, pardon my French. So this code makes use of spectral methods to solve the stellar structure equations in 2 dimensions. So the stars divided in what we call domains, and so the edges of the domains align with isobars. And so in each domain, the equations are discretized and then solved in each domain separately with the appropriate boundary conditions. And so the very powerful thing of Aster is that it can compute the velocity field in a self-consistent way, something you cannot do with 1D models. And so with velocity field, I mean the differential rotation that you get from the baroclinicity, so the misalignment of the pressure and the density gradients, as well as the meridional circulation, so the large-scale flows that happen because a deformed star cannot be in equilibrium anymore. Yeah, so lastly, I want to mention that this code is it's also publicly available if you want to have a look at it yourself. So Aster is initially designed to to compute what we call steady state models. So the kind of rotational evolution that has been done with these steady state models in these works here. What these models entail is that for those, we don't account for viscous effects or only in a very tiny layer at the surface to kind of break the degeneracy in the solutions of the rotation profile that we get. And then the evolution is emulated in a sort of sense so you have one value of the hydrogen mass fraction in the core, one value in the envelope, and you just have a discontinuity step function in between. And then so artificially you lower the hydrogen in the core according to a sort of integrated energy output. So we made some advancements on that, and so now moved on to what I call full 2D stellar evolution models. So what we do now is also actually solve for the diffusion of hydrogen, so that's the XDT term right here. So this depends on a term that's attributed to the meridional circulation. So this V is the velocity field. A diffusive term, and a term due to the nuclear reactions. And so in 2D, this diffusion coefficient is a tensor that has a horizontal and a vertical component. For the horizontal one, we take a constant value. And then for the vertical component, we use a prescription of rotational mixing that originates from the work of Zahn in the 90s. So what this means is that you scale the vertical diffusion coefficient with the thermal diffusivity and the gradient of the rotation profile. And this whole thing is then averaged over the theta coordinate, over the angular coordinate. And so in this theory, the diffusion coefficient also scales with the universal frequency. But for the 2D models, it's right now a bit too challenging to also have the effect of the chemical gradient that comes back into this universal frequency to also take that into account. So what we do is take a volume average at the SAMs and keep that as a constant. And then eta is another constant that is order unity. So that's what we put in physics-wise for the rotational mixing. Similarly, we also solve now for the angular momentum transport. So again, the term due to meridional circulation or inflection, and a term due to, or that's driven by the turbulent viscosity. And so this is again a free parameter in our models. So the turbulent viscosity gives a sense of how efficiently angular momentum transport is, or how efficiently angular momentum is transported in these models. So now I'm going to sneak in a little bit of F-type seismology, just to give you an idea that what we pick for this turbulent viscosity is not completely arbitrary. So I'm going to introduce the gamma Doradus pulsators. So these are F-type stars that have gravity modes that allow us to measure the core rotation or the near core rotation rates of these stars. In addition, a subsample of those are hybrid pulsators that have acoustic modes or rotational modulation, and from that we can also get the rotation rate at the surface. So this is kind of more tricky to do for higher mass stars, at least to get the rotation at the surface in combination with with the near core rotation rate. So for this sample from Ganglios, you are slowly rotating Gamma Doradus stars, and in the end, I managed for 6 of these stars to get constraints on the mass, the age, and the rotation frequency from the literature. So I use these stars as a sort of calibration point to see what the efficiency of angular momentum transport should be. So for these kinds of stars, if we plot the difference in the pulsation period between 2 modes that have a difference in the number of radial order of 1, and you plot it as a function of the period itself, you get what we call these period spacing patterns. And so the rotation induces a tilt in these kinds of patterns. And so if you have enough observed consecutive radial orders, in reality, then you can measure the slope and you get the near core rotation rate. So likewise, these pulsations also depend on the age of the star. So as the star evolves, they become more densely packed, and the periods themselves shift as well. So from this way, by modeling the individual periods, if you have enough of them, you can also constrain the age and likewise the mass as well, in combination with some other parameters like vector temperature and luminosity. So I'm here showing you an example of one of these stars. So the differential rotation, so the difference between what we measure from the gravity modes and the rotation at the surface is about 3%. And so for this this star, the isoseismic age is estimated to be close to 10. So it's almost at the edge of the plot. And so if we then compute, so these are still 1D Meson models. If we compute a bunch of models that have the same mass as the isoseismic estimated mass, and then see if we can, what viscosity we would need to reproduce the differential rotation at the estimated age of the star. So we assume that the viscosity is constant throughout the radiative envelope. And so here, as you can see, we need about a viscosity 10 to the 7 centimeters squared per second to reproduce the differential rotation in the star. And so in general, these stars have a differential rotation that's below 10%. So for the whole sample, find something that's within this range. So I'm kind of taking a higher limit of 10 to the 7 centimeters squared per second as the viscosity that we assume in the 2D STR models. All right, so that's kind of the physics that goes into these models. I'm now going to show you that we can reproduce at least one star. So that's always a good thing to do. So for this star, it's that is Cepheid pulsator. It's a massive pulsator. And the great thing about this star is that it has rotationally split modes that can be identified. And so from the splitting between these modes, we can derive constraints on the rotation profile. So the splitting is set by this integral here, where the rotational kernel K you can get from the models as well as this beta coefficient. So this allows you to put constraints on this omega R profile. And so and the star is quite unique in that sense that we can have a lot of data to do this. But yeah, so the thing is that people, it's not very clear what this omega R should be in massive stars. So what's typically done in literature is to assume a rotation profile like this sketch here. So you have a rotation rate in the core, you have a rotation rate at the surface, omega surf, and then you assume a sort of linear transition between the two from the radius of the convective core up to the radius what we call R shear. So you can place that, for example, at the edge where you still have a lot of mixing just outside the core. You can place it at where you have a zone where you have a gradient in the chemical or the mean molecular weight, or put it, for example, at the edge of the envelope. So these were three options that were tested for this star. So here I'm showing you got one of the first attempts to actually do full 2D stellar evolution with a mass that corresponds to the astroseismic mass estimate of the stars. It's 12 solar mass. It's not very rapid rotator, so this one is initialized at 15% of the critical rotation. So for STER, what we do is we initialize our models at the ZAMS as a chemically homogeneous model, steady state model, and then let it evolve from there. So yeah, just gonna run the GIF. So what we see in panel A is just the evolution track in the HRD, where the black dots are the effective temperature at the pole, and then the blue ones at the equator. And in panel B, we have the 2D rotation map scaled with the critical capillary rotation rate. In panel C, the sort of 1D cutout of this 2D map, where the green dots are sort of angularly averaged rotation profile. Here the diffusion coefficient, what we predict from rotational mixing, as I mentioned earlier. And then in the last panel, we have what we call the stream function. And so this shows you how the cells of the meridional circulation look like. And so here the red and black colors indicate oppositely rotating fluid elements. So what we see first is that as the star evolves, if you look at panel B, that it starts to evolve to a more shallower rotation configuration. And you can also see that in this panel where the blue and the black lines are kind of starting to converge to the same model. And so if we look at the mean rotation profile, we find that it's actually closest to, if I go back one slide, to putting this R shear radius at the edge where you have the mu. So the edge where you have a chemical gradient still as because of burning of hydrogen inside the core. And so another thing to mention is that in 1D codes, that's typically assumed is that this meridional velocity field can be modeled with a quadrupole. And so as you can see at the first stages of the main sequence, is not actually the case in these 2D models. Predict something differently. And then, yeah, once you go to a more shallow rotation profile, it starts to converge more towards a quadrupole configuration. But yeah, it's the 1D assumptions might not be fully correct compared to what we find with these 2D models. So the evolution of these stars is kind of driven by two competing timescales. So on one hand, we have the nuclear evolution timescale. So this is the timescale in which the hydrogen mass fraction inside the core changes. So this kind of sets the expansion rate of the star. And then on the other hand, we have the timescale on which baroclinic modes are being damped. So this gives you the timescale how efficiently, or the timescale on which angular momentum transport can take place. And so this depends on your Bruns-Fazal frequency, the rotation profile, thermal diffusivity, and the width of the radiative envelope. And so if this the barrow is larger than the nuclear timescale, it means that we can actually not do evolution by using a succession of these stationary models that I talked about before. So in that case, also, if you have high enough rotation rate, it will always evolve towards critical rotation rate. And so from these full 2D models, we see that this is not always the case. So in this case, for this star, at the first part of the main sequence, we find that this time scale is smaller, but then at the end, it becomes in fact larger. But yeah, this learns us that we should actually do full 2D stellar evolution and not just do a succession of these stationary models. So what we did for this star is from this evolution track, pick the model that has a hydrogen mass fraction in the core that is similar to the astroseismic estimate, and then see if we can reproduce the inferred core and the surface rotation rate. So that's what you see in this plot. So the black line is the rotation profile that we get from our best matching STR model. This is the radius of the convective core, and then the shaded regions are the uncertainties on the observational constraints. So you can see we do a pretty good job actually to reproduce these two quantities at the age of the star. And in addition, also the observed luminosity and the effective temperature are consistent with the observations. And the age that we find, as well as the core mass, is also consistent with the estimates from 1D modeling. But yeah, I note again that this is not incredibly fast rotating star, but it's a good calibration point because here also the 1D models are most likely still valid. Yeah, so I'll just make some notes on the chemical transport. So one commonly used scheme to do rotational mixing in 1D is based on many of these works listed here. So what this means is that you have this vertical diffusion coefficient. So that's the same one I mentioned earlier that also goes into the STR models, but then in addition, you have this effective diffusion coefficient that scales with the amplitude of the meridional circulation velocity field. But so if we look at the 2D models, so there we don't approximate this in a diffusive way, but do this self-consistently. So if we look at the amplitude of the velocity field in the vertical direction, so it's almost the same as the radial direction, let's say, we find amplitudes that are quite low, so 10 to the -4, -3 centimeter per second. So that gives us clues that what we find in these 2D models is that the chemical transport by meridional circulation is in fact quite inefficient. So yeah, useful thing to kind of observationally calibrate the efficiency of mixing tools to make use of the CNO cycle. So this is a cycle of catalyst, and the slowest reaction rate is the conversion from nitrogen to oxygen. So what that means is you start burning hydrogen in the core, you start to build up nitrogen 14 there as well. And so if you have efficient mixing, you can transport this towards the surface where it could be observed. And so indeed, we find stars that have enriched values of this nitrogen at the surface, indicating that there is efficient mixing going on. So in these models that I presented here, we've already accounted for this cycle here, so the conversion of oxygen towards nitrogen, and right now also working on implementing this other cycle, also taking carbon into account and solving the full diffusion equation for all of these species. So carbon, nitrogen, and oxygen, the most important isotopes. And so in these models where, so right now it's limited to this cycle right here, which is the most dominant one that dictates how fast you build up nitrogen inside the core. And so we find for these models, even for 50%, that we don't find any significant nitrogen abundance at the surface. But yeah, so this is kind of still future work. I want to do this in a more detailed way for a larger range of masses, where you also do have a more proper implementation of the whole CNO cycle. Okay. So yeah, for the last part, I want to talk about what these 2D models actually imply for the formation of single BE stars. So as I mentioned before, if these stars can form if you can form a BE star during the main sequence without the need of a companion, how do you spin up a star towards critical rotation, or what are the conditions needed to do so? So for this, we have computed 2D STR models within a range of 4 till 10 solar masses. So I'm kind of limiting myself right now to 10 because we cannot do mass loss yet. So it's also something I'm currently working on to implement in the code. But for now, I stick to 10 solar masses. And so here I'm showing you also the distribution of the angular momentum inside the star per domain, just to show you that the deeper layers contain the most angular momentum. So for this mass range, I would say it's pretty safe to neglect muscles. But yeah, it's a future work to actually account for this and push it towards higher masses. And so yeah, if I say critical rotation, I mean the Keplerian critical rotation rate, which is defined like this. So here I'm showing you the results. So here you see the evolution tracks of the Astaire models color-coded by the fraction of the critical rotation. So we stop them once they reach critical rotation, or if they reach critical rotation. So we've done this once for a metallicity that's representative of the Milky Way for different initial rotation rates, and once for a metallicity that's representative of the small Magellanic Cloud. So as a comparison, I also show in gray non-rotating MESA models, 1D MESA models, and in this panel here in blue, also the rotating cyclist tracks with the same initial rotation rate. And so for these 1D models, actually, they don't spin up to critical rotation, while for our 2D models, we find that in some cases they do. But it's a bit more interesting to maybe see it in this way. So here I'm plotting the fraction of critical rotation rate versus the main sequence H. And so yeah, we've done this once for 60%, 75%, and 90% critical rotation rate at the SEMs for different masses. So what we find is that actually something quite interesting. So the lower mass stars seem to still spin up towards critical rotation rate, and then you go to higher masses. So here for 6 solar mass, we find that they, well, it still increases a bit, but they don't spin up to full critical rotation rate. So if we then start with a larger initial rotation rate, so 90% even, we find that for 6, we can also push it towards critical rotation during the main sequence. But even for this initial rotation rate for masses above 8, we've observed that they always decrease their fraction of critical rotation. And so here at 60, it's not efficient to even spin up the lower mass stars. So yeah, it's quite interesting. These 2D models predict that there's a sort of threshold in mass and in the initial rotation rate where you can still push a star towards critical rotation rate. So, and where the lower mass stars still manage to do so, but then higher mass stars don't. So if we can kind of try to compare this to observational trends. So I'm showing you here the results from 2010. So these are V sin I over the critical rotation rate for different mass bins for non-emission line stars that have also no radial velocity. And so what these authors find is that the upper limit seems to decrease as a fraction of this V sin I over the critical if you go towards higher masses. So that's what I'm showing you in this plot here as the stars. So these correspond to these lines right here that I just showed. And so if we compare that with the average fraction of critical rotation normalized by the initial one for our models. So it's a bit maybe difficult to comprehend first, but so if it's above 1, it means that on average, the star will increase its fraction of critical velocity. If it's below 1, it will on average, spin down. So I'll say spin down, what I mean is the fraction of critical rotation rate. And so what we find is that we see a sort of similar trend in this quantity with respect to mass. So we find that the higher mass stars have on average a much lower fraction of their initial critical velocity compared to the lower mass stars. So we see a sort of similar trend. It's a bit it's not very trivial to make a one comparison with these observations, but it's kind of reassuring that we see that the most rapidly rotating non-emission stars have a sort of similar mass trend than what we predict from our models. So as I said, we've also done this exercise not only for galactic stars, but also for metallicity corresponding to the SMC. And so we find some interesting things there as well. So what we find if we go to lower metallicity, we find that we can also spin up stars of a higher mass. So year 6, we also, well, I guess it's barely critical that it goes to. We also see is if we compare the ages at which point these stars should reach critical rotation rate, we find that in lower metallicity environments, they reach critical rotation faster if they do. So this is summarized for these kinds of, if we go to lower metallicity, we manage to spin up stars of a higher mass and also in a smaller time frame. So if we would compare this to observational fractions of BE stars, so I'm here just showing you 2 plots from Ganada et al. So just focus on the solid data points, which presents the bona fide BE stars. So it's fraction. So this is for galactic metallicity, and this is for SMC metallicity. So what we find, for people to find in that is in lower metallicity environments, there seems to be a much higher or clear peak in the fraction of BE stars. And so if we look at the age where it is, it's about 50, 40-ish mega years. It's also seen to be kind of in line what we predict with the 2D models, or at least where we would predict some of the stars to reach critical rotation. And in fact, also, we expect also stars of a higher mass to spin up. So naively would expect indeed to have a higher fraction of B stars in lower metallicity environments. So that seems to kind of be indeed what is observed. So I also don't want to mention that this kind of metallicity dependence is in general not seen in 1D models. So the only models where seen that there's a metallicity effects are those from Hastings. But this is caused by the dependence on the mass loss. And so here I just repeat that we haven't done any mass loss yet. So this is pure based on the evolution of the 2D models, or the time scale on which the angular momentum transport is operating. So for the last part, I just wanted to mention also the uncertainties in our model. So as I mentioned before, we take the effect of the chemical gradient that comes back in the Bund-Fasel frequency as a constant value, and we have still free parameter of order unity in our models. And so here just showing you 2 examples. If we change eta in order unity, our predictions are still robust. We're not super dependent on the exact value of this eta as long as it's of order unity. So that kind of brings me to my conclusion. So we've done a first successful calibration of 2D stellar evolution structure and evolution models of rotating stars. And so in these models, we predict that what we predict from the self-consistently velocity fields for the meridional circulations is that they're quite different from what 1D schemes seem to predict with their assumptions. For the 2D models, we see that there is sort of threshold in the mass where lower mass stars manage to still reach critical rotation during the main sequence, but for more massive stars, it seems to be impossible even if you go to very high initial rotation rates. And so in general, what we find is that the rotational evolution of these 1D models so far seems to be in line with what is predicted or seen in observations of single PE stars. And then lastly, so it stars above 8 solar masses, we don't seem to manage to reach critical rotation during the main sequence. So this can mean a few things. So either the way we treat angular momentum transport in these models doesn't work for some reason, and for these for the spectral type, either the critical rotation at which these stars can lose mass doesn't need to be critical for higher mass stars, or that the single star formation channel just doesn't work for the most massive PE stars. Yeah, so with that, I'd like to thank you for your attention. So if you have any questions, feel free to ask. I'm also happy to hear any suggestions if you have any ideas for further calibrations of these 2D models compared to observations. Thank you.
Okay, so let us thank our speaker, Joey, for a great talk. And we'll open it up to questions. I see a lot of clapping hands, emojis in the among the participants. Does anyone have questions for Joey? Okay, so I might use my prerogative to open up the question period, and so this I'll preface by saying this might be a slightly naive question. I'm still a bit new to the BE star field, but I think that last point that you mentioned in the conclusions is actually quite interesting, and you know, kind of going into the realm of speculation a little bit. Would you be able to comment a little bit on, you know, obviously, I think you've shown the validity or the possibility of a single channel for the formation of these stars, but obviously both channels probably exist and they have relative contributions. So, could you say a few words about that, and also how like the mass loss would play into that for the higher mass stars and change that picture?
Yeah. So what we see now from these models, it seems that at least for lower mass stars, so let's say below 8 solar masses, it might still be possible indeed to form single PE stars, but above, it seems that even at very high rotation rates, it's always decreasing its rotation rate. So I would say if we can sort of trust these models, at least seems to be evidence that at least for higher mass stars, it might just be the binary channel, but for lower mass stars, there could indeed still be the possibility of the formation to the. Sorry, yeah.
Sorry, no, so maybe just to clarify, so have you made any attempt to kind of couple your models with population synthesis models to see what kind of expected frequency you would get from the single channel, and therefore be able to quantify the relative contribution of both channels?
Yeah, that's a good question, and I something I definitely want to do. But yeah, I'd like to note that doing evolution in 2D is much harder than doing it in 1D. So we're not really at the stage that we can compute like a massive grid that is required to do population synthesis, but it's indeed something I would like to do in the future. But there still need to be some improvements on the numerical aspect. Yeah, to do this, and like I said as well, to that was also related to your first question, actually, to include mass loss as well. So yeah, that will also slightly change the evolution of the critical rotation rate over time.
All right. Any other questions from the audience? Let me check the chat to make sure that I'm not missing something. Oh. Ah, yes. Okay. So we have a couple of questions in the chat. Sorry, I I wasn't seeing it. So first of all, there was a question from Grigoris. So I don't know if you want to unmute yourself and ask it, or I can just read it. But basically, any idea of the mass loss mechanism?
Yeah. Okay. Thank you. So what I want to ask is if there is, I mean, if you would like to include mass loss, do you have any idea of the mechanism to implement?
Yeah, so what we try to do right now is use a prescription that is based on the CAK mass loss. So I'd also refer to the paper of Damien Gagné that I mentioned before. So there they tested this as well. But yeah, not in the feedback of evolution that I would like to do. But in this prescription, you have a mass loss that depends on the 2D structure of your star. And then once you have that, you'll integrate over the surface to get the integrated mass loss and then adjust the mass accordingly. But yeah, the approach would be to use this kind of CAK mass loss prescription, if that answers your question.
If this can solve for this difference in the mass loss at the equator, in the sense that since you have the formation of the disk, you would expect that the mass loss there should be a bit higher than the poles, right?
Yeah, indeed. Yeah, you'll have a mass loss that is dependent on the angular coordinate theta. But yeah, then there's again also the question of mass loss once you reach critical rotation. So the mass loss, yeah, due to the star being at critical rotation.
Okay. Next up, we have a question by John.
Hey, great talk. Lots to think about here. So I was wondering about a scenario where you might have binary mass transfer that spins the star up to, 99% of critical or something. And then after that point, the star would essentially evolve as a single star, right? So I'm wondering, would your results maybe imply that the more massive stars, maybe the BE phenomenon is more transient, the evolutionary pressure doesn't allow them to stay very close to critical, versus the lower mass stars, if they're spun up via binary mass transfer, they have an easier time like maintaining their status as a BE star, like until the end of the main sequence?
Yeah, that's a good question. So yeah, if we would assume indeed that once mass transfer has occurred, that the star can be modeled with these kinds of single star evolution models, we would expect that they slow down indeed. So so that's maybe something that other people in the audience can answer better, but I don't really know. So once a disk is formed, how long it could stay if the star then decreases its critical rotation rate. So yeah, I guess the time scale in which such a disk would dissipate, yeah, is needed to predict indeed. If we can have these stars that, yeah, sorry.
Oh, no, that was it. My bad.
Okay, yeah, sorry. But yeah, so like I said, again, it would be then interesting to have predictions on if you could form a disk and then spin the star down while still having a disk.
Yeah, like it seems crazy to start a star on the zero-age main sequence at 100% of critical, but if you imagine zero-age main sequence as immediately after mass transfer, that could be interesting to see, yeah, what happens.
Yeah. But yeah, I also don't know if the just internal structure is significantly different compared to if you just take a single star evolution path.
Yeah, no clue here.
Okay. Are there any other questions, maybe specifically from junior members of the audience? I see one in the chat from Patrick Stanley. Patrick, I don't know if you want to unmute or...
Yeah, sure. I can unmute.
Okay, go.
Yeah, I know classical BE stars haven't been found in magnetic. but there are a few cases of rapidly rotating magnetic stars. So I was wondering if there's any plans to include magnetism into your models to see if you can reproduce any of those results.
Yeah, so that's in fact going to be a whole 6-year ERC synergy grant called 4D Star. So there, the idea is actually to also even go to 3D or the 3 spatial dimensions, and then the idea is indeed to also include the effects of magnetism. But that's quite an ambitious project.
Great, thank you.
Other questions? So if no other junior members have questions, I know that Connie maybe had one.
Yes, thank you. And of course, I have opportunities to ask many questions. I just wonder, Joey, something I haven't asked yet. It's about the calibration that you take from astroseismology on the n0 squared. I mean, you showed that it doesn't really matter if you have a small change, but if I look at the astroseismically calibrated Brunt profiles, as you know, they can change dramatically across the domain sequence at least. So have you also tested, like, if you change this n0 squared times eta with a factor 10 to 100, how that impacts your results?
Yes, I did play around a bit with that. The issue is also in STR, it's still quite difficult to explore a large range. So if we go quite far away from these values, it becomes numerically unstable. So it kind of limits me as well in testing right now what the effect would be. But yeah, I think for a factor 10 as well, you still get qualitatively the same conclusion.
Okay, because of course this changes dramatically as the star evolves. So anyway, maybe it's something. Yeah, we have
I
to.
hope at least that we in these stars have enough sufficient mixing that you don't get a very big spike near the core. So averaged out over the main sequence, it might not change too much. But yeah, I agree that in the future it would be nice to see if we can improve on this.
Okay, we need seismic modeling of pulsating BE stars. That's the conclusion, right?
Also, but yeah, it's mostly like a numerical issue for now to account for this. So even in 1D, it's actually quite challenging to do.
Yeah. Okay. Thanks.
Okay, great. Are there any other questions? We still have some time if people have more questions for Joey. Last call. Yes, Dietrich.
John already said, and I would like to follow up on what John said and ask, since after the mass transfer, the BE stars seem to be evolving as single stars, whether you can explore the threshold, how much angular momentum you need to have at the beginning of this rejuvenated evolution of the rejuvenated star to make it rotate nearly critically. Because there is some consensus in the BE star community that the BE phenomenon has, quote unquote, the purpose of enabling BE stars to remain intact, that they are not rotationally distorted, they're destroyed. And there is some mechanism that ejects the matter, but the angular momentum loss associated with a loss of matter is critical for the survival of BE stars. And so it would be very interesting if you repeated your calculations with a very high initial rotation rate, which is not consistent with the evolution of the formation of singles or with the evolution of stars that have formed as single stars. And then I could imagine that your models could have an important bearing on what BE stars really are.
Okay, yeah, so if I understand correctly, you would like to have a model that starts almost at critical rotation and then see what fraction or angular momentum transport you would need to sustain this.
I wouldn't give a prescription for that, but that you lift the plausibility restrictions on the initial angular momentum of your model. Because a binary does not comply with these constraints. You can dump an arbitrary amount of angular momentum or specific angular momentum on the BE star, which then evolves as a single star after the mass transfer. So whether this is critical or 80% critical or 70, that is something one would also have to explore by models so that you just can tell us from when on can your single stars then reach critical rotation.
Yes, yeah, I see. But in some sense, that's not what I kind of showed. So we have different initial rotation rates at the SAMs and then see in which cases they spin up.
Yeah.
But yeah, I guess for the binary, you might indeed have a different distribution, initial distribution of the angular momentum transport. Yeah, so yeah, that's something I don't know on top of my head if indeed once you have mass transfer, if the angular momentum transport is then redistributed so fast that we can say that the rotation profiles is similar to what we expect from a single star evolution. But I agree, yeah, it's an interesting exercise.
That's of course the first thing to be explored, yeah, whether the rotational profile of a star after angular momentum transfer has anything to do with the rotational angular momentum profile of a single star, of an originally single star. Yeah. But if there is some similarity, that one could perhaps use your models to see how these stars evolve as effectively single stars after the mass transfer.
Yeah, I see.
And that would be attractive, I think.
Yeah. But I think in some sense, what I showed you here, you can just see the angular momentum transport that we assume at the SAMs and then see how these models evolve further out. If we assume that the angular momentum transport or the distribution is similar to a SAMS star, a single SAMS star.
Thank you.
But yeah, thank you for your suggestion.
Any more questions? Okay, so I think we've had a pretty good discussion here and maybe some food for thought as well. So let me thank again our speaker, Joey, on behalf of everyone.
Thank you as well.
This was a really great talk. I'll also mention to everyone that we'll be taking a break for the summer. So the next seminar will be held in September. So stay posted. We'll send the details for that later this summer. So thanks again, everyone, for attending. Thank you, Dr. Mombarg, for a great talk. And I wish you all a great summer or winter, as the case may be. And take care.
Bye-bye.